Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in. We are going to go through everything you need to know from semester 2. Now, I'm going to try and keep this a short video, A, because I know you don't want to hear me for 40 minutes, and B, because I've made revision videos for the other tests. So, for example, the test we did in term 3 on index laws, I made a revision video for that. So if you want a more in-depth review of the material covered, you can find that video or you can email me if you want the link. All right, let's start off with the first topic. So I'm doing these in the order that I taught them to my class. So first off is statistics. Of course, is just concerned with collecting and analysing data. So you need to know the mean, median and mode. So remember, the mean, colloquially referred to as the average, is just add up all the scores, divide by n, and is the number of scores. So the median is the middle point of the data. Sometimes there is one middle number, sometimes there are two. Now, if you have heaps of data points, heaps of scores, the median is n plus 1 on 2. That's the number of the score that is the median. So, for example, if there were 31 scores, 31 plus 1 on 2 equals 16. So the median wouldn't be 16, it'd be the 16th score. It doesn't matter whether you consider it the 16th highest or 16th lowest. Remember that you find the middle point when the scores are in order, from smallest to largest. So the other one we need to know is the mode, and the mode is the easiest of all to find. It's just the most common, but do remember that data can have no mode if no scores are repeated. It can have two modes, we say it's bimodal. More than two modes, we call it multimodal, or it can be unimodal. So let's go ahead and look at an example. Okay. So we've got 6 scores here, and I've just put them in order for simplicity. So the mean of this data, you add them all up, you get 90, and you divide by how many there are, so the mean is just 15. So the median, because there are an even number of scores in this case, the median will be the average of the two middle scores. So these are the two middle scores. So halfway between them, if you don't know what that is, you just add them up and divide by 2. So that gives us 15.5. So the median is 15.5. So mode, in this case, there are two modes. There are two most common numbers, 14 and 17. I need to write both. And because there are two modes, I say it is bimodal. Okay, fantastic. Now we're going to have a quick review of skewness. So when we're talking skewness, we're going to look at histograms. So remember, histograms has to involve numerical data, a score along the x-axis and frequency along the y-axis. So we have bars for each score or each class of scores, and a higher bar means it occurred more often. It has a higher frequency. So in the one I'm drawing at the moment, you can see there are a high frequency of scores closer to the minimum, and that's what we call positively skewed. It sort of goes in the opposite direction you'd expect. You might think positively skewed, there'd be more positive, more higher scores, but it goes in the opposite way. Okay, so we'll draw up another frequency. So if we have the opposite, where the higher frequency scores are closer to the maximum, then we say the data is negatively skewed. In this one here, by the way, it's bimodal because there are two modes, two most common scores. So this one would be negatively skewed. So if data is neither positively skewed nor negatively skewed, then we say it's symmetrical. Now, symmetrical usually means there's a higher frequency of scores closer to the middle. So you might expect something like this. However, that isn't always the case. It can be symmetrical even if it doesn't have a higher frequency of scores closer to the middle. If you have something like this, this would be symmetrical. So it's not the middle that has a higher number of scores. You can see there are 3 peaks here, okay? So this one's just not negatively skewed, not positively skewed. Therefore, it is symmetrical. So it's not always clear cut which of these it is. There is a mathematical way to determine skewness. We're not going through that. For you, just look at the histogram and make sure you have a reason for saying it's positively skewed, negatively skewed, or symmetrical. All right, the last thing we'll do is look at comparing data. So let's say we've got a list of scores of two groups, in this case boys and girls, and we want to compare them. So a good way to compare them is to draw up a back-to-back stem and leaf plot. So it's just like a normal stem and leaf plot, but you have two groups here. Okay, so here we need scores in the 60s, 70s, 80s, and 90s. So we always make sure that the data is ordered, and it allows us an easy comparison. Okay, so looking at this data here, we can also determine skewness. So boys, we'd probably say is symmetrical because there's not a higher frequency of scores close to the minimum or the maximum. For girls, there's a higher frequency of scores closer to the maximum, so we'd say they're negatively skewed. Remember, a stem and leaf plot is basically a histogram on its side, and you group the data in tens. So this helps us look visually at who did better. It looks like boys did better, but let's go ahead and calculate the mean and the median. So we'll start with girls. So for the median, note here, again, there are 6 scores. If I use the formula before, 6 plus 1 on 2, and plus 1 on 2 gives me 3.5. So that means the median is the average of the third and the fourth scores. So third and fourth scores, halfway between 85 and 87 is 86. So make sure you realize this score isn't 5, it's 85, okay? And we do so for the boys as well. So third score, fourth score, so the median is 86, okay? So they both have the same median. Let's look at the mean. So if we add up all the scores, we get 509. There are 6 of them, so the mean is 84 and 5, 6, or 84.83 recurring. Okay, so that's for the boys, and for the girls, we add them all up. So they add up to 481, and if we divide that by 6, we get 80.16 recurring, or 80 and 1/6. Okay, so even though they have the same median, the boys have a higher mean, and therefore we'd conclude that boys did better. Okay, so we'll now go and look at probability. Okay, so hopefully we know by now that probability is the maths of assigning to an event a number to indicate how likely it is to occur. So the number that we give the event is always between and including 0 and 1. This statement reads the probability of an event is between 0 and 1. Obviously, if we give it a number closer to 1, that means it's likely to happen. If we give it a number close to 0, it's unlikely to happen. So the theoretical probability, that's what should happen. That's the proportion of times we expect that something will happen. So the probability of an event is just the number of ways the event can occur over the total number of outcomes. But remember, there's also experimental probability, and this is also known as relative frequency. And to find the experimental probability of an event, it's just the number of times that the event occurs over the total number of trials, okay? So it's pretty simple stuff. So for example, if I roll a die, and let's say I do this 10 times and I get 7 6s. So in that case, the experimental probability of getting a 6 happens 7 out of 10 times, so it's just 0.7. But the theoretical probability, that would still be 1 over 6. So hopefully we can see from this, the experimental probability and the theoretical probability are not necessarily equal. So theoretical probability is what should happen, and relative frequency or experimental probability is what actually happens. So when we say the probability of rolling a 6 is 1 over 6, the theoretical probability, we mean that we expect that if we roll a die heaps of times, 1/6 of the time we should get a 6, whereas the experimental probability is saying, well, we don't always get it 1/6 of the time, it's the proportion of times it actually happened in a number of trials. All right, next up we'll look at Venn diagrams and two-way tables. Okay, so let's look at this example here. 30 students, 20 play AFL, 15 do rowing, 7 do neither. Find the probability a student plays either AFL or does rowing. So this is where we might use Venn diagrams and two-way tables. Now, these are just tools that essentially do the same thing. Unfortunately, you need to know how to use both of them. So they're very useful when we have more than one set. So we've got a set of students who play AFL, a set of students who do rowing. Okay, so what we have to do is put it into a Venn diagram or two-way table first, and then we can answer the probability question. It'll make the question a lot easier. So remember Venn diagram, we've got a rectangle and two circles that represent the two sets. In this case, we've got AFL and the number of students who row. So you probably noticed that 20 plus 15 plus 7 equals 42. That's 12 too many. So we've overcounted 12, so we put 12 in the middle, okay? That's the only possible way the numbers can add up to 42. So 12 people do both, but there were 20 who play AFL. So there's another 8 who play AFL and don't row. There's another 3 who do rowing but don't play AFL. Okay, and then 7 do neither. That should go outside. So these numbers, 8 plus 12 plus 3 plus 7, should add up to the total number, which is 30. And they do. So we could have just as easily put this in a two-way table. So the two sets, again, we have AFL, and we also have people who don't play in AFL. That dash means not. And, of course, the other option is that the students row or do not row, and we just populate this table. So the number of people who play AFL and row, again, that's the number we've overcounted, so that's 12. Row but don't play AFL, so that's these people here, 3. These people play AFL, so they're in this column, but they don't row, so we put them here, and then 7 do neither. Now, normally in two-way table, we also have rows for the total just to help us along. So here we'd have 20, 10, 15, 15, and these two numbers and these two numbers should add to the same thing, which they do, 30. So we know we've done something right. So now we've got a Venn diagram and a two-way table. Answering probability questions is easy. So it's a probability that a student either plays AFL or does rowing. In maths, when we say or, we pretty much always mean one or the other or both. So we mean what's the probability a student plays AFL or rows or both. Now we can get the answer from either the Venn diagram or from the table. So we've got 8 plus 12 plus 3, which is 23 out of 30, okay? And in the two-way table, it corresponds to these three numbers here. So the probability is 23 out of 30, okay? So this would also enable us to answer other probability questions, like what's the probability that a student plays AFL but does not row? That's not immediately obvious from the information given. So the probability that a student plays AFL but does not row, that would just be 8 over 30 or 4 over 15. Okay, so two-way tables and Venn diagrams just help us with probability calculations. I'll now go through tree diagrams. So tree diagrams are useful for displaying all the outcomes of multi-stage events that occur in stages, like tossing a few coins or rolling a die, then tossing a coin or whatever. So I'll show you the example of tossing 3 coins. We'll put in a tree diagram, it'll give us all the outcomes. So we have the first stage, which is the first coin, second coin, third coin, and then afterwards we list all the outcomes. So, first time you toss a coin, obviously you get heads or tails. If you get heads first, you can still get heads or tails, and so on. So doing the tree diagrams isn't too difficult. So it will give us all possible outcomes by following the paths. So what I mean by that, so we've got heads, then heads, then heads. We follow that path, that's our first outcome. And then we have heads, heads, tails, heads, tails, heads, and so on. So you can see here that there are 8 possible outcomes. Yeah, we might have been able to list them without a tree diagram, but tree diagrams just help us with that. So all of these outcomes are equally likely because at each stage, head or tail is a 50-50 chance. It's half probability. So I did teach my classes instances. We did tree diagrams when each outcome wasn't equally likely, like you had, a bag of marbles, 5 red, 4 blue. So we're not going to go into those in the test. We're just going to look where all of these outcomes are equally likely. So there's 8 of them, so each of them has a probability of occurring of 1/8. So this allows us to answer probability questions about multi-stage events. So if I toss 3 coins, what's the probability I get all 3 heads? So there's only one such outcome out of 8. What would be the probability that I get at least one tail, for example? So we can count them. 1, 2, 3, 4, 5, 6, 7 outcomes have at least one tail out of 8. Easy as. So we need to know the difference between with replacement and without replacement. So this one is an example of with replacement. The reason is it's like if we toss a head the first go, it's like we replace the head. So we can still get it on the second go. So then we have instances where, you'll get something on the first go and you can't get it on the second go. That's without replacement, and I'm now going to show you an example of this. Okay, so this is the example that I'll give you. I have a bag that has a Mars bar, Boost, and Crunchy, and you get to pick 2 of these at random. So if you pick a Mars bar first go, you don't put it back, you keep it, so then you can't get a Mars bar second go. That's why this is without replacement. So if you get something first go, it's not being replaced. So we'll do the tree diagram. So there are 2 stages to this because you're picking 2 chocolates. So you can get Mars bar, Boost, or Crunchy first up. But if you get a Mars bar first, you can only get a Boost or a Crunchy next time. Okay, so again, we do this so we can list all the possible outcomes, and that will make probability calculations nice and easy. So these are the 6 outcomes, and they're all equally likely, and that means that each of them has probability occurring of a 6th. So we can use this to answer probability questions. So for example, what is the probability that I do not get a boost? Let's go and look at the outcomes. There's 1, 2 outcomes that do not have a boost. So it's 2/6 or 1/3. Okay, what's the probability that I get, say, a Mars bar and a Crunchy in any order? Doesn't matter whether I get Mars bar first or Crunchy first. We can see that that is exactly the same, 2/6. It's the outcomes that I've circled. Okay, so again, tree diagrams, all they're good for is just listing outcomes to help with probability. Make sure you know the difference between with and without replacement. All right, I'll now go through all the index laws that you need to know. Okay, so hopefully you know that if you have something like this, the thing that's being raised to a power is called the base, and the thing to the power is called the index. That's where we get the name index laws from. So you need to know all these index laws. So firstly, if we multiply bases together, we add the indices. Second one we learned, if you divide bases, you subtract the indices. We also learned that if you raise a power to a power, you multiply the indices. We also learned that if x is not equal to 0, then x to the power of 0 equals 1. So that means 1 to the power of 0, 2 to the power of 0, 3 to the power of 0 is all 1. We also learned a couple with brackets. So if you have something like xy to the power of 5, you raise the first thing to that power and the second thing to that power. And if you're raising a fraction to a power, then you just raise the top thing to that power and the bottom thing to that power. So that's some, very, very simple examples. Sometimes you'll have to use a couple of index laws. So for example, let's say we have something like 2x cubed to the power of 6, okay? So we're using this index law here and this index law here. So we need to raise 2 to the power of 6. People often forget to do that. And then x to the power of 3 to the power of 6, we multiply the bases. How easy is that? We might have something like x to the power of 12 times x to the power of 9 divided by x to the power of 15, for example. So that would be x to the power of 21 using the first index law, and then we use the second index law. Remember, this fraction line means divide, so we would just subtract the powers, okay? So if you want more of an in-depth look at the video I've already made. Now I'm going to give a very quick crash course in scientific notation. So remember, in scientific notation, we take a really large or really small number and write it as something times 10 to the power of something. So let's say we have a really big number like this. So if I want to write it in scientific notation, I take the decimal point, which is at the end of a whole number, and I move it until the number is between 1 and 10. This number has to be between 1 and 10. So if I do that, the number becomes 7.34652. So I write that number times 10 to the power of, and the number of places I move the decimal point goes in the power. So I moved it 6 places here. So if I want to round to significant figures, remember this number before the decimal point counts as a significant figure. So to 3 significant figures, this would be 7.35. I increase this one because this one is more than 5. 7.35 times 10 to the power of 6. That's the answer to 3 significant figures. We also do similarly for very small numbers. So if I have something like 0.0003125, I move the decimal point until the number becomes between 1 and 10. Write that number times 10 to the power of. Now I moved this one 5 spots, so I put a 5 there, but because I moved the decimal point to the right, because this number is less than 1, it's a negative 5. So both of these are now in scientific notation. If I wanted to round this to one significant figure, it'd just be 3 times 10 to the power of negative 5. Fantastic. We'll now look through similarity. So remember that two shapes are similar if all of their angles are equal, pairs of corresponding angles are equal, and pairs of corresponding sides are in the same proportion. So let's say I've got two shapes here and I'm going to make them both rectangles. So they will have all angles equal to 90 degrees, so they satisfy the first criteria. If I make this 4 and this 3 and this 6 and 4.5, then these figures are similar. So all the angles are equal, the sides are in proportion because 6 divided by 4 equals 4.5 divided by 3. And that number that they both equal, 1.5, is called the scale factor. So what that means is I've pretty much taken the first shape and enlarged it by a factor of 1.5. I've multiplied each side by 1.5. So shapes can be similar even if they're not triangles. So these shapes here are both similar. So we can use the fact, if two shapes are similar, we can use the fact that the scale factor is the same for all sides to find unknown sides. So let's look at an example. Okay, so I'm going to tell you that these two shapes below, both of them are pentagons. I'm telling you that they're similar. We can only do what I'm about to do if the shapes are similar. So first thing you do is find the scale factor. So when you've got two shapes next to each other and you have to find an unknown side, I've said that it's easier if you do the scale factor as the larger side over the corresponding shorter side. The reason for this is then it's clear that we always multiply to find a side in the larger shape and we divide to find a side in the smaller shape. So let's start off by finding x. X is in the larger shape. So x is just corresponding side times the scale factor, and you get 5.25. Y is in the shorter side, so it will be the corresponding side divided by the scale factor. Easy as. Now we'll go and look at similar triangles. So triangles are a special case. We don't have to check that every pair of angles is equal and that every pair of sides is in the right proportion. We can just use one of the tests. So the tests are very similar to those for congruence. So we have SSS. So here S means a side in proportion. So if all three sides of two triangles are in the same proportion, they will also have pairs of corresponding angles equal, and therefore they will be similar. SAS, so two sides in proportion and the angle between them is equal. AAA, this is the only one that's different from congruence, and then RHS. So it is a little confusing. When we say A in these tests, we mean that a pair of angles is equal, and when we say S, we mean pair of sides in proportion. Note that for the test that involves sides, you need at least 2 pairs of sides to be in a proportion. You can't have just 1 pair of sides being in proportion. That doesn't make sense. So you'll need to look at examples and decide which of these tests fits. So let's say, for example, I give you these 2 here, and I say 4, 4, 5. Okay, so these sides are in proportion because 7.5 divided by 5 is the same as 6 over 4. It equals 1.5. So these two are similar by the SSS test. Now, what I've said in other videos as well, if you have no information about the lengths of sides, or you have insufficient information about the lengths of sides, it's always AAA. So if I give you an example like this, these two sides are parallel. This smaller triangle and the larger triangle, they are similar by AAA. And we know that because there's no information about lengths of sides. This angle is common. These two angles are corresponding, so they're equal. And these two angles are also corresponding. If you have 2 pairs of equal angles, you must have 3 pairs of equal angles, because angles in any triangle add up to 180 degrees. So again, we can use this to find unknown sides and angles. So let's look at an example. Okay, so let's look at the 2 triangles here. So we can't assume lines are parallel unless they're marked. Fortunately here, these are marked, okay? So there's still insufficient information to use any of the tests involving sides, because this big triangle, I only have the length of 1 side, so I can't possibly have 2 pairs of sides in the same proportion. So this again is AAA. These 2 angles are equal because they're vertically opposite. These 2 angles are equal because they're alternate. We have parallel lines, and similarly for those 2 angles. So in the test, we're not actually going to prove that 2 triangles are similar, but we still need to be able to understand why they are similar, even if we don't do a formal proof. So to find what x is, we have to find the scale factor. So the confusing thing here is which side corresponds to 6. Is it this side or this side? So the way you might look at it is, see, 6 has the x and the dot. So I need to find the corresponding side in the smaller triangle that has the x and the dot, and that's this one here. So actually 6 corresponds to 2, not to 3. So the scale factor is 6 over 2, which is 3. So x is a side in the larger triangle. So x will just be 5 times the scale factor, which is 15. How easy is that? All right, I'll now go on to our last topic of quadratics and their graphs. So the first thing we need to know how to do is expand binomial products. So binomial products where you have the 2 brackets and you have 2 terms in each, something like x plus 2 times x plus 3. So the method you can use is FOIL. So remember, first, outsides, insides, last. So firsts gives you x times x. We're timesing everything, remember. O is outsides, so x times positive 3, then insides, and then lasts. So you need to collect like terms as well. 3x and 2x are like terms. Now there are quicker ways to do this if you don't want to use FOIL. So if I have something like this, x minus 4, x plus 9, for example, so this is monic because the number in front of both the x's is 1. So multiply the 2 x's together. Now the number that goes in front of x is the sum of these two. Minus 4 plus 9 is positive 5, and then the number that goes by itself is this times this, which will give you minus 36. There are other ways you can do quick ones. So remember, something like x minus 2x plus 2, there's the same thing in each brackets, except one has a minus, one has a plus. This is a difference of 2 squares, so you just square the first, square the second term, stick a minus between them. If you have a perfect square, like x plus 5 squared, people always get mixed up. They'll say it's like x squared plus 25. Well, that's not quite right. There's a middle term. So what you do is you square the first, you square the last, but in the middle goes 2 times the product of the 2 things inside. So 2 times 5 times x gives you 10x, okay? If I change this to a minus, so it's x minus 5 squared, it'd be x squared minus 10x plus 25. Last term is always positive in a perfect square. So let's go and look at factorization. So as you saw in the examples that I just gave, when we expand, we start with brackets and we end up with something without brackets. So factorizing is the opposite. We start off with something like this, and then we have to write it as something times something. So in the test, we're only going to look at binomials that have two terms. So there's two options, highest common factor or difference of two squares. Some actually involve both. So x squared minus 9, there's no common factor here, so I know it's difference of two squares. So this is what you do, square root the first term, square root the second term, one gets a plus, one gets a minus. If you have something like x squared plus 5x, well, that's definitely not the difference of two squares. It's got a plus, and this term has an x, so the highest common factor goes out the front. What do I times by x to get x squared? What do I times by x to get positive 5x? So if I expand my answer, I should get what I started with, because expanding and factorizing undo each other in exactly the same way multiplication and division undo each other. So if I have something like 2x squared plus 6x, here the highest common factor is 2x. What do I times by 2x to get this? X. What do I times by 2x to get this? 3. Easy as. So if I have something like 4x squared minus 121, well, this is difference of two squares. That's a perfect square. That's a perfect square. So then square root the first term, square root the second term. One bracket gets a plus, one gets a minus. So I'll show you an example where you have to use both. If you want to try something like 2x squared minus 288, the problem is that 2 is not a perfect square, 288 is not a perfect square, but they do have a highest common factor. So I always try highest common factor first. So the highest common factor is 2. So what do I times by 2 to get this? Just x squared. What do I times by 2 to get this? It's just minus 144. So to factorize this fully, I know this is the difference of two squares. So it'll just be 2 x minus 12, x plus 12, easy as. Okay, now we'll look at solving quadratic equations. So to solve quadratics, always use these 3 steps. Sometimes they'll be done for you. So make one side equal to 0, then factorize, then use the null factor law. And the null factor law is that if two things, a and b, multiply to 0, either the first thing is 0 or the second thing is 0. Let's look at an example. So if we have x squared minus 6x equals 0, so one side equals 0, first step done. We then factorize. So this is highest common factor. We haven't changed it, we've just factorized. Now we use the null factor law. We have something times something equals 0. Either the first something equals 0 or the second something equals 0. And if x minus 6 equals 0, x equals 6. Let's say we have, x squared equals 16. So we can subtract 16 from both sides. So now we have one side equal to 0. And then we factorize here using the difference of two squares. So either the first thing equals 0, which means x equals 4, or the second thing equals 0, x is negative 4. So just note that quadratics sometimes have one solution and they sometimes have two solutions. So we're just looking at solving ones with binomials again, either using highest common factor or difference of two squares. So the very last thing I need to show you is how to graph. So remember, an equation is quadratic if it has an x squared term. If it's y equals something times x squared plus something times x plus something. So a quadratic equation, when we graph it, is a parabola, and it looks like that or that. They all have the same basic shape. So this is the way I taught it in my class. I said find 4 features of the parabola. So you can find the orientation, whether it's a smiley face, which is like the first one, or a frowny face. Second thing is find the y-intercept. There's always one. Secondly, find the x-intercepts. That's hard because you have to solve a quadratic. There could be 0, 1, or 2 x-intercepts. And fourth is you can find the turning point and the axis of symmetry all at once, okay? So you find the y-intercept by letting x equal 0, x-intercept by letting y equal 0, and for the turning point, the x-coordinate is minus b over 2a. So b is the number in front of x, and a is the number in front of x squared. So let's look at an example of this. So let's say I want to graph the equation y equals x squared minus 9. So firstly, the orientation is a smiley face if the number in front of x squared is positive, and if a is negative, the number in front of x squared is negative, it's a frowny face. So this one will be smiley face. Second thing, y-intercept. So if x equals 0, y would just be 0 squared minus 9. Okay, so that, of course, is just minus 9. That's the y-intercept. To find the x-intercepts, you let y equal 0. So if 0 is x squared minus 9, we solve this just like I solved on the previous slide. So factorize, and then use the null factor law. Either the first thing equals 0 or the second thing equals 0. So here there are two x-intercepts. So for the turning point, so here the number in front of x is 0 because there's no term with x in this. So the turning point will be x is 0 because b is 0. So that's the x-coordinate of the turning point. It's also the axis of symmetry. And if x equals 0, y equals minus 9, as we figured out before. So the way we graph this all, draw up our Cartesian plane. I'm just going to do a rough sketch of this. So x and y, same meaning as they've always had. So you mark all the intercepts. So y-intercept at minus 9, and the x-intercepts are at negative 3. And of course the other one is at positive 3. Now I know that it's going to be this way, so all I have to do is join them up because all parabolas have the same basic shape. And that is the graph of y equals x squared minus 9. Okay, I'll do one more example where we use highest common factor rather than difference of two squares. Okay, so I'm going to find the four things that I mentioned on the last slide. So firstly, the number in front of x squared is 1, positive, so it's going to be a smiley face. Second, y-intercept, I let x equal 0. So y would be 0 squared minus 3 times 0, just 0. Y-intercept is at 0. Thirdly, to find the x-intercepts, so I let y equal 0. So I have x squared minus 3x equals 0. Factorize, and then use null factor law. Either the first thing is 0 or the second thing is 0. So I have two x-intercepts again at 0 and 3. So to find the axis of symmetry, I use x is minus b over 2a. So here b is the number in front of x, which is minus 3. So minus b is minus 3 over 2 times a. That just gives me 1.5. In fact, the axis of symmetry is always halfway between the two x-intercepts, if there are two x-intercepts. So let's look at the graph again. I'll just do a rough sketch here. So we have the orientation, easy. So I know that the y-intercept is the origin. It goes through 0. The x-intercept is also there at the origin, and there's also 1 at 3. And halfway between them at 1.5 is the axis of symmetry. And the turning point is there as well. So if x equals 1.5, the y value will be 1.5 squared minus 3 times 1.5, and if you put that on your calculator, it's minus 2.25. We didn't really need to calculate it in the last example because we knew where the turning point would be because it was at the y-intercept. So it goes down to y is minus 2.25. That's the turning point here. I'll plot that. So I know it's going to be this orientation, and it goes through the 3 points I've marked. So I just join them up, and that is the graph of y equals x squared minus 3x. Sorry for the long video, and I hope you get something out of it. Best of luck in your exam. This has been the luckiest maths teacher in the world. Have a great day.